Okay, problem number 1 on the review for Chapter 7. According to the Dumont Global Automotive Color Popularity Report, 23% of all cars manufactured in the current year are white. A random sample of cars parked in a long-term parking lot at Philadelphia International Airport reveals that 19% of the cars were white. Which statement is true? Okay, so let's kind of think about what's the population, what's the sample here. So this is talking about 23% of all cars manufactured in the current year. So all cars manufactured in the current year is the population. The 23% must be talking about the population. So 23% is a parameter. So it might be one of those. 23% is not a population, right? A parameter describes a population. Population is all cars manufactured. A random sample of cars parked in long-term parking lot in Philadelphia, 19%. So a sample, 19% is a statistic. So, they're definitely not both of that. So it's got to be B. Perfect. Below are dot plots of the values taken by 3 different statistics estimating the same parameter in 30 samples from the population. The true value of the population parameter is marked with an arrow. So here's that arrow right there. So it looks like it's probably talking about the mean, I'm guessing here. It doesn't say what the parameter is, but it looks like that does seem to be pretty close to the mean of that first set of data, pretty close to the mean of the second set of data. I'm not sure where the mean is, but I think it's to the right of that for this data. So which one has the most bias? So the first two seem to be unbiased, or at least that's my guess here. But the last one, C, is would be biased, right? Because the population mean and the sample mean do not match. If they do match, it's unbiased. Unbiased estimator. Okay, so factory produces plate glass with a mean thickness of 4 millimeters and a standard deviation of 1.1. A simple random sample of 100 sheets of glass is to be measured. The sample mean thickness of the 100 sheets X is computed. Which of the following is closest? Probably the average thickness of the 100 sheets is less than 4.1. So the mean of X bar does look like there's a sample. So mean of X bar is thickness of 4. Standard deviation of X bar would be the 1.1, which is the population standard deviation divided by the square root of 100. Because there's a random sample of 100, so divided by 10, so that's 0.11. So this is going to be 4.11, 3.89, I believe. And you can keep going there. Let's see, it says we want it to be less than 4.1. So 4.1 is right in there somewhere, so 4.1. So we want that value or less. We want less than that. So I think you would get your calculator out at this point. Go menu 652, norm CDF. So lower bound, that seems good at negative infinity. 4.1. Mean is 4. Standard deviation is 0.11. So it should be 0.8183. So A is your answer there. Simple random sample of 100 is selected from population 1, which follows a normal distribution with a mean of 40 and a standard deviation of 4. Independent simple random sample of N2 is 85, is selected from population 2, and follows a normal distribution with a mean of 25 and a standard deviation of 7. Which of the following expressions represents the standard deviation of the sampling distribution of x1 minus x2? So are these means, are these proportions? So it does seem like they are means here. Okay, so you're hoping it needs to pass that less than 10% condition. Since there's no option for no other, I think it seems to pass that condition. So so then the formula is the square root for means, square root of standard deviation squared divided by, and I believe plus standard deviation squared divided by n, where this is like the first one and this is like the second one. Okay, so which one looks like of that form? So plus, this guy's plus, this is not it. This is definitely not it. They don't have the same dimensions. That's definitely not it. You don't even really have to, you know it's going to be A there. If you just know the formula, even it's the only one that really looks like that form. According to the Humane Society, 39% of households in the United States have at least one dog. In the United States, 23% of households have at least one dog. Suppose you select the simple random sample of 75 houses in the UK and 80 houses, a simple sample of 80 households in the UK and calculate, US, sorry, 75 in the US and 80 in the UK. Calculate the proportion of households in the US that have a dog and the proportion of households in the UK and the sample that have a dog. Which of the following best describes the mean variability and shape of the distribution of P hat 1 minus P hat 2? So it does look like, let's see. So it doesn't say anything about the shape of the original population, but we are taking samples of size 75 and 80, which are, so we have to do NP, right? This is proportions. So let's check the proportions here. So NP must be greater than or equal to 10 for the, say, the US. So for US, N is 75 times US is 0.39. And we're hoping that's going to be greater than or equal to 10, or that equals something, but it's going to be greater than or equal to 10. We'll type that in the calculator in a second. 75 times 0.61, that'll be failures, should equal something. That should be greater than or equal to 10. And then for the other one, we're going to do the same thing. So it's going to be 80 times 0.23. And we're hoping that's greater than or equal to 10. And 80 times 0.77. And we're hoping that is greater than or equal to 10. So let's get our calculator out and just check those. 75 times 0.39. That's bigger than 10. 75 times 60.61. That's bigger than 10. 80 times 0.23. Bigger than 10. 80 times 0.77. Bigger than 10. So you would write all those numbers down there. And that proves that it's normal. So this one's gone, this one's gone. So A and D are gone. Oops. So the mean, so we're doing P hat 1 minus P hat 2. So P hat 1 is the US. So US was 0.39. So it'd be 0.39 minus 0.23. Which is 0.16. So this one is gone. Mean is not unknown. Standard deviation. So let's see if we can figure out standard deviation. So we've done this test, so we know it passes that, all those, right? So we can do the standard deviation formula, which is the square root of PQ. So P is 0.39 times 0.61. all over N, which was for US, I believe, 75, plus 0.23 times 0.77, and in the UK they had 80. So you would try to type that in. You gotta be careful, type that in. Type the square root first. Control divide for the fraction. So 0.39 times 0.61 all over 75 plus control divide 0.23 times 0.77 over 80. 0.0733. So 0.073. So it's got to be E. Doctor claims that women are less than 5 feet tall tend to live at least 100 years old. That's interesting. The dot plot below shows the results of the average lifespan of 150 simple random samples of size n equals 10 women that are under 5 feet tall, selected from the records of government-issued death certificates. Is there convincing evidence that the mean lifespan of women is less than 5 feet tall in at least 100? So we want them to be living longer, right? So by the way, these look like they're going by twos, so 98. This is 100 is right there. Those 3 dots right there would be where 100 is. I don't know if that'll help. Okay, so just look at the simulation. There's 150 there, 150 simple random samples. So each one of those dots is a different simple random sample, right? There's 150 dots there. Each one represents the mean of 10 women that they selected. So it looks like 1, 2, 3. So if you draw the line right before that, so 1, 2, 3, 4, 5, 6, 6 out of 150. How unusual is 6 divided by 150? So that's the question. 6 divided by 150 is 4% chance. So just by chance alone, in the simulation, we simulated the results. It's only 4% of that happening by chance. That these women are living more than 100 who are on the shorter side. So this is unusual. I don't think that's happening. In fact, it says if you look at 6D, that looks very tempting. No, only 4% of the simple random samples show an average lifespan. We do not have enough evidence to conclude that less than 5 feet tall evidence. So I think that's true. So unfortunately, if you're below 5 foot tall, you might have been hopeful, like, oh, I'm going to live over 100. You still might, but there's only evidently about a 4% chance. So it's not very likely. Right now, we don't have an evidence to back up this claim. Maybe future studies could, but that we don't have it now. Sampling distribution of statistic is, so just what is a sampling distribution of a statistic? So sometimes you can kind of eliminate answers. The probability we attain with this repeated random samples. Sampling distribution, that's what we did with the pennies, right? We took a sample of like 5 pennies and averaged them and plotted that, and we made a sampling distribution. So I don't think A just doesn't sound right. The mechanism that determines whether randomization was effective. Again, I don't think it seems right. The distribution of values taken by a statistic in all possible samples of the same sample size. So I like that, all possible sample size. That's what I think of with the sampling distribution, right? So you're doing every possible case. The extent would differ from the truth. No. The distribution of values in the sample size of n, that's at least tempting. Distribution of values, I think that would be the distribution of the sample. These words do get confusing, but I'm quite sure it's C actually. But it helps to read all the answers and get rid of the, I mean, I think to me, I'm debating between these two if I'm debating. Some of those weren't close to the answer there. But I like, if you do all possible samples, you're guaranteed an unbiased estimator there if it's like a mean or something. According to a recent poll, 27% of Americans get 30 minutes of exercise at least 5 days each week. Let's assume this is the parameter value for the population. If you select a simple random sample of 25 Americans and let p-hat be the proportion of the sample who get 30 minutes of exercise at least 5 days per week, is the shape of the sampling distribution going to be approximately normal? So what's the condition we have to check? So we want n to select the sample of 25. Ooh, so 25, these are means. Well, let's see. So actually, these are proportions, aren't they? So if it was means, you go, oh, you got to just, look at this. What is this? These are proportions. So the condition we have to meet is the NP has to be greater or equal to 10, and then Q has to be greater than 10. So N is the number of samples, which is 25 times 0.27. We're hoping that's at least 10, and then 25 times 0.73. We're hoping that's at least 10. So let's try that. So 25 times 0.27 and 25 times 0.73. So unfortunately, right, this guy is only 6.75. This doesn't pass the test. That's not at least 10. So I would say B. No, because, you know, we didn't get it. And it would help if n was a little larger, right? A larger n really helps you pass this test. If n is only 10, it's going to be tough there to get it to work. Or n was, I guess, 25, but it's still on the relatively small side. Bigger than 30, we might have a better shot. Okay. 9, the histogram below was obtained from the data on 750 high school basketball games in a regional athletic conference. It represents the number of three-point baskets made in each game. So there were 300 games-ish where one three-point basket was scored. There were no games where no three-point baskets were scored. Mrs. Phelps selects many simple random samples of size n equals 40 from this population and calculates the mean number of three-point baskets. Which of the following best describes the shape of the sampling distribution of the sample means? So this should be piece of cake. Oh, wait. You got to read it. If you're not paying attention, you go, it's just describing that. But this is definitely skewed right? The population there. But we're taking a sample of that with a sample size of 40. Are these means or proportions? These are means, right? The mean number of three-pointers made. So if we take sample size 40, well, that's at least 30, which means the central limit, the CLT, kicks in. And this should be approximately normal. I believe 9 should be D. The CLT, central limit theorem, refers to the following characteristic of the sample distribution of mean. Regardless of the shape of the population distribution, the sampling distribution of the sample mean with sufficiently large samples will be approximately normally distributed. Actually, that sounds pretty good. I'm leaning that towards that one. Regardless of the shape of the population, the standard deviation of the sampling distribution will be, no, that's not always true, right? We need n to be at least 30 if we don't know what the population looks like. The mean of sampling distribution would be sufficiently large samples will be equal to the mean. I don't think, like, there's some parts of that sound good, like the sufficiently large, but not the equal to the mean of the population. As you select larger and larger samples from a normally distributed population, the standard deviation of the sampling distribution mean gets smaller and smaller. Ooh, wait. So that is true. That's a true statement. So is that what the CLT is saying? That's just a concept. I don't know if we have a name for that, but it's a concept that happens. But I think this is about the shape, CLT. So I'm leaning towards A here. A is correct. As you select the larger, the mean is, okay. So again, we're not really talking about any. So it's confusing because D is actually a true statement, but it's not the CLT, right? So study of college freshmen study habits found that the time and hours the freshmen study each week followed a distribution with a mean of 7.2 and a standard deviation of 5.3. So it doesn't say it's normal there, I don't think. Okay. So can you calculate the probability that the randomly chosen freshman studies more than 9 hours? If so, do it. If not, explain why not. Okay, so why not? Well, you would say we don't know the shape of the sampling distribution, right? We don't have enough information. If the population was approximately normal, then we would know the shape. Or if we knew the sample size, wait, so we just don't even, we're not even taking a sample here. I misspoke there. So we don't know the shape of the population. We can't just norm CDF it because, which is what we want to do, but we don't know if the population is normal or not. So we don't know what the shape is. So you can't do it. That's why. We don't know if it's normal. So what are we supposed to do? What is the shape of the sampling distribution of the mean weekly times if the sample of 55 randomly selected freshmen? So that's more than 30. We are talking about means here, mean number of hours. So it's more than 30. So we think it's going to be would be approximately normal because 55 is greater than or equal to 30. It passes the test to be approximately normal. calculate the mean and standard deviation of the sampling distribution of the mean weekly stay times for a sample of 55. So what's the mean going to be? So the mean is going to be 7.2. The mean of X bar is 7.2. And the standard deviation of X bar is going to be a fraction, 5.3 up top, divided by square root of 55. So then you would type it in your calculator, 5.3 divided by square root of 55 is 0.714652. So C should be 715. You got it. Yeah, perfect. And not a bad idea to put hours here. Right, 7.2 hours, just the context of the problem. Sometimes it's easy to forget little stuff like that. Always a good idea to do that. Okay, so we would draw the normal curve here, 7.2. Again, if you want to quickly kind of figure out what the three are, 7.2 percenter, we're going to add the standard deviation 3 times. So we get 7.9, essentially 8.6, 9.3. And then if we type 7.2, oops, get over there, 7.2, and then subtract the standard deviation, if I can get back up there. So we get 6.5-ish, 5.7-ish, and 5.05. Okay, so we've got our graph there. We want to get greater than 9, so somewhere over here is 9 right there, and shaded to the right. So then you would get out your command, menu 652. Lower bound would be 9. Upper bound is infinity. I'm just going to type a big number. Mean is 7.2. Standard deviation is, I believe it was 0.714. So I got 0.5% or 0.0058. Yeah, perfect. I was just making sure I was right. Yeah, we were right. Okay. According to a poll, 22% of high school students in the United States say that Dobby is their favorite character in the Harry Potter books. Let's assume that this is the parameter value for the entire population of high school students. Mrs. Lewis selects a sample of 150 high school students and records the population p-hat of individuals in the sample who say Dobby is their favorite character. Calculate the mean and standard deviation of the sampling distribution of p-hat. Okay, so looks like we have, this is proportions. Sample size 150 here, so that's good. That's good size. So the mean, so let's see, the mu of p hat is going to be 0.27 or 0.22. I mean, check the less than 10% condition. So NP. So this would be N would be 150 times 0.22, and then 150 times 0.78, and those both have to be at least 10. Type them in your calculator, and I can tell they are going to be. I'm not going to type it in, but you would do that. Okay, so it passes the test, which means we can do the standard deviation. So I think it's standard deviation of p hat is going to be equal to its square root pq over n, so 0.22 times 0.78. all over n, which is 150. I'm doing these formulas from my head, so hopefully they're right. I think they are. Not a bad idea to use your formula sheet. Control divide is a fraction, so 0.22 times 0.78, all over n, which is 150. So 0.033. Yep, that looks all right. What is the approximate shape So what do we have to check the condition for checking the shape for proportions? So proportions, you know, I think I did this test, which should be for this one. I should have checked that we're sampling less than 10% of the population here. So 150 is less than 10% of high school students, all high school students in the United States. Yes, 150 is less than 10% of all high school students. So it passes the test, so we can do standard deviation. This test is for normality. So it's good to get that straight. The large counts condition checks for normality. So what's the approximate shape? Because it passes this test, both of them are greater or equal to 10, we would say it's approximately normal. Always use the word approximate when you're using the word normal. Just a good idea. Suppose our sample size was 36 instead of 150. Okay, so that's not as big a sample. So there's going to be more variation. It's not going to be quite as normal if it is normal for the shape, center, and spread. So it still passes. We can calculate standard deviation. So it's going to be square root of standard deviation of p hat. Square root of, so 0.22 times 0.78 all over 36. So if you do that, see what happens to standard deviation. It's kind of interesting, right? Maybe you can predict it. So that's a bigger standard deviation. It's more spread out, right? So this is 0.069. So if it passes the NP and NQ, so let's do that. So if we do, instead of 150, it'd be 36 times 0.22. It's not approximately normal, right? So so we have the shape, center, and spread. So the center would be 0.22, right? The shape we're not sure about. The spread is this, right? So let's look at 12, what it says here. So the mean would not change. The standard deviation would be larger, and the sampling distribution would be non-normal. So that's all we know. I was trying to see, like, do we know what the shape would be? We just know it's not normal. So this is not normal. Non-normal, not normal. Okay. 13. According to figures in the U.S. News and World Report, 54% of Penn State University, 41,000 some students are male, and 48% of University of Pittsburgh's 19,000 undergraduate students are male. There's more females in college, that's true. Suppose a random sample of 100 undergraduate students was selected from both Penn State University and University of Pittsburgh. And so let P hat PS be Penn State proportion, and then proportion of males, and then same thing for that one. Okay, so describe the shape, find the mean, find the standard deviation of the sample distribution of the difference of those two. Okay, so this is a good problem. Okay, so find the shape. So what does it say about the shape? So it's a random sample of 100. So to test the shape, we've got to do the NP. So NP has to be greater than or equal to 10, and we have to do this for both things here. So so 100 is for both times 0.54, and then 100 times 0.46. That's for the first goal. And 100 times 0.48. And 100 times 0.52. Those all have to be at least 10. I can do that in my head and say those are 54 and 46 and 48, 52. They're all at least 10. And you kind of knew that because anytime the proportion is near 0.5, usually passes this test. That's if it's near 0.1 or 0.9, like near 0 or 1, then you might not pass it. But you're going to usually pass it in this case. So it's no surprise. So we do think it's approximately normal for the shape. The mean shouldn't be too bad. It should be, we have to do Penn State first. So 54, so 0.54 minus 0.48 is 0.06. So that is the mean difference in the, so you would write it like the mean of x bar, no, p hat, Penn State minus p hat, University of Pittsburgh. And so you've got, you've got the 0.06 is that standard deviation, or that mean. And then standard deviation, if we check the less than 10% condition, so 100 undergraduate students is way less than 10% of each one of those goals. They're pretty big, I think. So you can do the formula, which is square root of PQ over N. So for the first one, that would be 0.54 times 0.46 over N, which is 100, plus 0.48 times 0.52, all over 100. And you type that in your calculator and you will get the standard deviation of, this is 13.071. I believe I set that up. So equals 0.071 when you type it in. What's probably that the proportion of males selected from Penn State is less than the proportion of males selected from University of Pittsburgh. So let's go ahead and draw our normal curve. So our mean is 0.06. The mean difference is 0.06. The standard deviation is 0.071. So you can go 0.06 plus 0.071. So 1.31. Or sorry, 0.131, 0.202, and so forth. This one, just go backwards one, so 0.06. Minus the 0.071. So this is negative 0.011, one standard deviation below. So we want to find out that it's less. So to think about this, so Penn State is less. So right now we're doing Penn State minus University of Pittsburgh. So if Penn State's smaller, we're tracking a bigger number. We want it to be negative, right? So 0 is right around here, so 0 is here. So shading to the left. So then you get out your calculator and make sure you write down the command. When you do this, menu 652 in your calculator, norm CDF, lower bound's negative infinity, upper bound is 0. Mean is 0.06, the mean differences, comma, standard deviation is 0.071. And you type that in your calculator. You should get, I believe, 0.1977. I didn't check that, but we should be okay. Identify the population parameter of the sample and the statistic in this setting. 2016 survey conducted by the Democratic Party 1 week before Election Day asked a random sample of 1,500 voters which presidential candidate they would vote for. Of the respondents, 54% said they would vote for the Democratic candidate. Okay, so identify the parameter, the sample, and the statistic. Okay, so the population, the parameter, and the sample and statistic. Okay, so population. So random sample of 15,000 voters from the presidential candidate they would vote for, of the respondents, certain percentage. So the population is all eligible voters in the U.S. It's really sloppy. You get the idea, though. You're listening. The parameter about the population is so the true proportion of those who are voting Democratic, right? So the true proportion of the Democrats. you're measuring that, right? So the sample is the 1,500 voters. So the 1,500 voters that were sampled, that were selected. Statistic is actually the 0.54, which is the proportion or percentage of folks who said they, in the sample, who said they would vote for Democrats. Okay, last question. Sample proportions. List all 6 possible simple relatives of size 2. So we could have, I'm just using abbreviations here, so red and white, red and silver, red and red. Oh, that's weird. Okay, and then which is 1 and 2, or 1 and 5, I mean, 1 and 8, and 1 and 20. And then let's do white and silver, white and red. I gotta think about that. Silver, silver and red. I think that's true. So it's confusing because there's, but I think those are different, right? So, okay, so then this was age would be the 5 and 8, the 5 and 20, and the 8 and 20. I think I forgot to do part of this question. So this is the sample proportion of red cars. It wasn't making sense to me. I don't think we need the ages at all. So I wrote down the 6 possible samples of colors there that we could get. Calculate the proportion of red cars in each sample. Okay, so I just hadn't caught on to that. So so the proportion of red cars in the first sample would be this first one. RW would be what's the proportion there? It's half. Half red and half white, right? So it's a possible case. So red and white. So red and white is 50%, so 0.5. RS is also 50%. RR would be 100% or 1. WS is 0%. WR is 50%. And SR is 50%. So it says to plot those on a dot plot, right? So we've got P hat, the proportion is the sample proportion of red cars. Remember the context, we're talking about cars here, or the color of cars. So if you plot these, there would be 0, 0.5, and 1. So 0.5 has a couple of dots, actually 4. 0 has 1 dot, and 1 has 1 dot. So something like that, pretty symmetric. Is a sample proportion an unbiased estimator of the population proportion? So the sampling distribution has a mean of 0.5. You can just kind of tell. You can see it's symmetric. The actual, actually there's 4 cars, right? There's 2 of them are red, so the population is also 0.5. So when the sample proportion and the population proportion match, you got your case of an unbiased estimator. So that is true. They're both 0.5. That's your lesson for today.